Hey everyone, welcome back to my podcast, Anatomy and Physiology Bit by Bit. I'm your host, Dr. Steve Sullivan, coming to you from Bucks County, Pennsylvania, just outside of Philadelphia, where I've been teaching A&P since 2002. Today we're moving on with the digestive system, discussing the small intestine, the pancreas, the liver, the gallbladder, and the chemical digestion of all the things we eat and drink. But first, recently I had the enormous privilege of speaking with Dr. Jessica Knurick, a registered dietitian with a PhD in nutrition. She also has nearly 1 million followers on Instagram, where she very successfully tackles disinformation about health, nutrition, and public policy in the United States. She sets the record straight on a wide range of topics using valid empirical data and scientific evidence. She is the real deal and backs everything up with valid sources. We talked about the difference between a dietitian and nutritionist. I think you're going to be really surprised on that one. What it takes to become a dietitian, high fructose corn syrup, nutritional myths, scientific and information literacy, social media, and the Make America Healthy Again movement. I'm going to post links to her Instagram, Substack, and website on the show notes, and I'll tag her on Instagram so you can easily find her. So without further ado, here is my conversation with Dr. Jessica Knurick. Okay, Dr. Jessica Knurick, welcome to the show. I've been following you on social media for some time and recently discovered your Substack. I am addicted and obsessed. You are fighting the good fight for scientific and information literacy, which quite honestly, despite the A&P stuff that my students need to know, that is my number one goal with my students, and I tell them that on day one every semester. So thank you for that. For the listeners who don't know who you are, would you mind telling us a little bit about yourself, your background, and what you do?
Sure. Thank you so much for having me. I'm excited to be here. So I have a PhD in nutrition science. I actually have a master's degree in exercise science and a PhD in nutrition science, and I'm also a registered dietitian. When I was getting my PhD through grad school, my research was really focused on chronic disease prevention, mainly looking at cardiometabolic disease. So things like type 2 diabetes and cardiovascular disease, kind of lifestyle related diseases, and looking at how we can reduce risk of those lifestyle related diseases. So when I was going through kind of that research, I was really focused on the individual and like, what can we do to optimize the health of an individual? And what I found was, we had good science about the actual strategies and nutritionally and lifestyle strategies that are best to improve health. But what the difficulty was the adoption of those behaviors. So behavior change. And the behavior change research is pretty clear that it's pretty difficult to get people to change their behaviors. So my research really looked at what is the lowest minimum viable thing that we can get people to do that can actually have a really meaningful impact on their health. And so we used things like a fiber supplement or walking after a meal and saw a pretty good result for risk reduction. And so, yeah, that was kind of my academic trajectory.
Oh, that's interesting. I also have an exercise science background. My undergrad was exercise physiology at Rutgers.
Oh, nice.
Yeah, so a lot of times when people would ask me, what's the best exercise that I can do for like losing weight or burning calories, and my answer is always whatever you'll actually do.
Yeah.
Because compliance was the number one barrier to whether or not something worked. So you're the first dietitian/nutritionist I've had on so far. So for all the students out there who may be interested in a career in nutrition, is there a difference between a dietitian and a nutritionist?
Yeah, there is. So a dietitian is a protected title in the United States, and this is very specific to the US. It varies around the world, but in the United States, to become a registered dietitian now, you need at least a master's degree. So when I went through, you needed a bachelor's degree. Now it's required to get a master's degree in nutrition science or a related field. And then after you've complete that, you have to do a supervised internship. It's 1,000 hours of an internship, so it usually takes around 9 months for most people. And you do kind of a rotation. You'll do clinical nutrition and community nutrition, food service management. I worked in school nutrition for one part of my internship, which was really cool. And so once you complete that, you sit for your RD exam through the Commission on Dietetic Registration. And so if you pass that, you become a registered dietitian. And then if you live in a state with licensure, so some states are licensed and some aren't, you get licensed in that state. And then you need to maintain that credential. So every 5 years, you need to recertify with, I think it's 75, I'm not 100% sure, but you need continuing education credits. So every 5 years, recertify. It's a healthcare position. On the flip side of that, a nutritionist is not a protected title, and so anyone can call themselves a nutritionist. Your next door neighbor can watch a YouTube video and about nutrition and call themselves a nutritionist because it's not protected. They don't have to have any actual formal education in that. That doesn't mean they don't, because there's PhDs in nutrition who didn't become dietitians, and so they refer to themselves as nutritionists, and they have a very extensive nutrition background. It's just that when somebody says that they're a nutritionist, you don't know what their background is. Whereas if somebody says they're a dietitian, you know their exact training.
That explains a lot of the people on social media who
Yeah.
are claiming to know about
Well, yeah,
nutrition.
and it's a bummer
Yeah.
because most people don't know the difference, so it's like they have no idea. So if somebody says they're a nutritionist, they're like, "Oh, that's great. Same as a dietitian."
Right. And I imagine that when most people think of a nutritionist or dietitian, they think of someone who's prescribing foods for patients or recommending foods to avoid based on a pathology that they have or their personal health goals. I actually had an optometrist on once who shocked me when he said that prescribing eyeglasses is only 15% of what he does. So, what would surprise people about a day in the life of a dietitian?
There's different paths to be when you become a dietitian. You can work in clinical, like in a hospital, which a lot of dietitians do. So that's a big part of the dietetics program is clinical dietetics. And so you work on medical nutrition therapy, and that's something that only dietitians are legally allowed to do. So nutritionists can't do that. A lot of other professions can't do that. Things like tube feedings, they'll work on tube feedings for patients who need tube feedings or TPNs for ICU patients. They'll work with people who have diabetes or kidney issues or even burns and trauma. So you go through a lot of schooling in clinical nutrition like that and doing things called medical nutrition therapy. You can also work in more like disease prevention and health promotion and health policy. That's kind of like the field that I'm most interested in. So that's kind of working in public health, shaping policies on things like food access or chronic disease prevention, nutrition programs. A lot of them work in like SNAP Ed, which is the Supplemental Nutrition
Mm.
Assistance Programs, and working on education in that field, working with WIC and school meals. You can do those types of things. Some dietitians work in research, so they're research dietitians, and they work in clinical research and non-clinical trials because a lot of clinical trials in the nutrition field require a dietitian to kind of create those meal plans and work with the subjects within that. And then I have also seen, now there's more opportunity to work in like tech and work in startups. There's a lot of nutrition startups that look for dietitians to kind of bring them on board. There's a lot of these like apps and things like that. So there's a lot of like career opportunity within the dietetics field, and it's more than just working in the hospital, which I think a lot of us kind of think about when we think about dietetics.
Well, so it seems like if someone's interested in being a dietitian, once they get their degrees and credentials, it's like a choose your own adventure. There's so many directions they could go.
There's a lot of directions. You can even work in private practice. I didn't even bring up. So a lot of dietitians will just, if they're more entrepreneurial and they like to work for themselves, they can open up their own practice and work with people one-on-one. A lot of times they'll specialize in a certain area. So they'll do like GI health or something like that and kind of take on clients one-on-one. So yeah, there's a lot of different opportunities.
That's a great option for students who are interested in healthcare field.
Yeah.
So, if you don't mind, I want to shift gears to some practical nutrition. I'm sure you get a lot of questions about high fructose corn syrup. I'm one of the people who really tries to avoid it. Recently, I was at a conference and I saw a session by a researcher who discussed the negative effects of fructose, just in general. Mainly that fructose has an easier path to lipid synthesis than glucose because it doesn't require insulin to cross the cell's plasma membrane, which my
Hmm.
listeners already know about.
Okay.
So, can you discuss if and why high fructose corn syrup is worse than typical sucrose or table sugar, which also has fructose? And what does that mean for fruit? Should we be avoiding fruit?
Yeah, so there is evidence to show when we look at like animal models and you take fructose as a sugar, and I should just define really fast. There's three main monosaccharides, which are your single sugars, and that's glucose, fructose, and galactose. Glucose is really that sugar that all sugars break down to because it's the fuel for your cells, and then you have fructose, which is basically a fruit sugar, and you have galactose, which is a milk sugar. So those three sugars really comprise all of the sugar that we consume, right? Sucrose, which is table sugar, is about 50% glucose and 50% fructose. High fructose corn syrup instead of 50-50, the most common is 55% fructose and 45% glucose. So it's just 5% more fructose than what table sugar is. That's not meaningful when humans are actually consuming this. So the research that looks at fructose specifically, there is an easier path to lipogenesis, right? And that buildup of kind of fat in the liver, which can lead to insulin resistance. But that's very different than saying when we're consuming it in like normal adequate amounts, because most of those studies look at really high levels. They're looking at like mechanistic pathways for metabolism. And so that's what we find with fructose is it's a different pathway for metabolism than glucose, and it goes through the liver and can cause more lipogenesis in the liver. But again, when we're thinking of like what we consume, high fructose corn syrup, and by the way, we use high fructose corn syrup in the United States because we grow a lot of corn, right? And so we can use that as a sugar source. It's a lot cheaper to use than cane sugar. So that's why it's used more in the US than most other places because we do grow so much corn. And the problem with it is because it's cheap, it's used abundantly in ultra processed foods, mostly low nutrient ultra processed foods. And so it's not really the type of sugar is actually not really the biggest issue. It's the overconsumption of sugar in general, and over 50% of Americans overconsume added sugar. And so when we're thinking about this, it's really more important to focus on just like overall sugar consumption than the source of sugar that somebody's getting their sugar from.
Okay, that's good to know. That is really good to know. I actually, about 10 years ago, I lost about 30 pounds, and my main action was cutting out added sugars. Like that
Yeah,
was
yeah,
the
and
main thing
just
I did.
yeah, and I mean that's a great thing to like look at because most of the foods that contain added sugars are fairly low nutrient foods, right? And so you're kind of cutting out a good amount of those types of foods. And also, it's not that sugar is bad, like that. This is where the nuance comes in, right? We need sugar, and there is absolutely zero evidence to suggest that fruit is unhealthy for us. In fact, it's
Right.
quite the opposite, right? And fruit is obviously sugar. But with that sugar, you're also getting fiber and you're getting lots of nutrients. You're getting tons of water in the fruit. So the package it comes in is in a lot better package than, let's say, Skittles. So that's a big distinction.
Great. Thank you for clarifying that.
Sure.
Um, actually, I've actually had a couple of episodes early on in the podcast that I called Mythbusters A&P edition, dispelling myths like blood is blue on the inside of our bodies, or we only have five senses, or things like that that would drive me crazy that college students coming into my class would believe because their high school teachers told them this. And I can only imagine that nutrition is the world leader when it comes to people believing things that aren't true.
Yeah.
So, what are a couple of myths in nutrition that you find yourself having to dispel most often?
Well, the one we just talked about is one about
Okay.
fructose and just why it's used in sugars and things like that. I would say right now there's a huge narrative on social media around seed oils. Seed oils are basically oils that come from seeds, like safflowers and sunflowers and rapeseed, which we call canola oil in the United
Mhm.
States. This idea that they're unhealthy, which really flies in the face of nutrition science research. They are processed oils, which is where I think this comes from because it's very difficult to extract the oil. So they go through this kind of like major processing to get the oil out of the seed. And because of that, the nutrients are really stripped out of the oil. So unlike olive oil, which has some of these nutrients, right? It's more of a nutrient dense oil. Seed oils don't. But the thing is, with the fatty acid profile is really what we're looking at with these oils. And they're pretty abundant in polyunsaturated fatty acids. And when you look at epidemiological data, when you look at nutrition science, like long-term nutrition science data, you look at the populations who are consuming seed oils, there's no evidence to suggest that they are harmful for people. And in fact, they're used abundantly all around the world in a lot of countries that have really good health outcomes, right? And I'm not saying that's because of seed oils, but a lot of times you'll hear like us compared to Japan, for example. Well, I mean, the number one oil used in Japan is canola oil. It's not, they're just not the boogeyman and the harmful thing that a lot of people on social media like to make them out to be. Most of these things come out of a little truth, and that's what makes them so easy to believe and makes them kind of so dangerous and harmful too. Because there is some evidence that, like when we look at like in vitro studies and we look at like very specific mechanistic studies, that some of these polyunsaturated fats, again, when they're overconsumed or when we add a lot to it, that it can go through this pathway that can potentially impact inflammatory pathways. And so they kind of use that and then extrapolate that to say that that's happening in in the human body. And it's just that we don't have evidence to suggest that that's happening. And then another one that I would say is pretty prevalent right now is just this idea of our ingredients in the United States versus ingredients in other countries, particularly like around food dyes is a big one right now. And I think a lot of people think that we use synthetic food dyes here and they're banned all around the world. It's just blatant misinformation. When I clarify it, I'll get like kind of like feedback that they think that I'm pro food dye. And so I always just want to like clarify, I'm not necessarily pro food dye. I'm pro giving accurate information, right? And not fear mongering information. Like, let's talk about these things honestly. So there's 9 food dyes that are approved, synthetic food dyes approved in the United States. By the way, there's even more approved in the European Union. We have less approved here, but we use out of those 9, one just got banned. There's 5 of them that are actually used in the food supply pretty abundantly. So that's red 40, yellow 5, yellow 6, blue 1, and blue 2. All 5 of those are approved for use and deemed safe by regulatory agencies all around the world. EFSA in the European Union have deemed them safe, and they're approved for use in Australia and New Zealand, in Canada. And I think that might come as to be like surprising to some people because there is so much social media misinformation that these are banned in other countries and we're kind of like allowing people to be poisoned here. And that's just not accurate. So again, regulatory agencies all around the world have shown that in the doses that we are exposed to them, they're not harmful. The problem with them, of course, is that artificial food dyes are really used in a lot of foods that, me as a dietitian, I would recommend we consume less of, right? They're usually used in these ultra processed, low nutrient foods that don't have a lot of like redeemable qualities, like Skittles, for example, or like candies and sodas and things like
Fruit
that.
Loops.
Yeah, Fruit Loops.
Yeah.
And so they're used as a marketing tool for corporations. So corporations make what consumers buy. And unfortunately, in the United States, we tend to buy more of these bright colored foods, and we're drawn to more of those than other countries like in the European Union. So we tend to use them more here than other countries do. It's not because we allow things that other countries don't. I think that's the important distinction.
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
I'd like to talk about your social media presence. Everyone can find you on Instagram, TikTok, etc. I'm going to put links to all of them, including your website and Substack, in the show notes so people can check them out. I highly recommend, if you're not already one of the almost 1 million people following Dr. Jessica Knurick, you should be. I've been following you again for some time. I especially love the videos you make countering the disinformation that's running rampant on social media and in our own government. Somehow you manage to do it without being snarky or self-righteous, which I do not think I'd be able to do. So first, how long have you been doing this and what made you start?
Yeah, that's a good question. I had my son. I have a 5-year-old son. I had him in 2019, and I have a 2-year-old daughter who I had in 2022. And in between those two kind of children, TikTok kind of became big, right? And so what I saw was this big difference in, because when you're pregnant, you are kind of in this vulnerable life stage, and you're really targeted with a lot of misinformation on social media. Just becomes your entire algorithm is this information about pregnancy and postpartum. I saw a lot of misinformation in the nutrition space targeting pregnant women. And so that's actually what brought me to social media. It was in 2022. I was like on TikTok. I thought, hey, this isn't accurate. Like, let me go on and just kind of like correct some of these things and help people who are already stressed, already anxious, and at this vulnerable life stage. And I focused really on pregnancy for a couple of years. Then because again, that was the life stage I was in. I was just trying to kind of help dispel some of that. And then, as I kind of mentioned, my research focus has always really been in chronic disease prevention and also looking at like systems and kind of policy and how policy is impacting our food environment and what's available to us and how we can improve the health of Americans. And so the MAHA movement started, which was last summer. I started seeing kind of just like when I was pregnant, kind of that same type of misinformation, but targeting my exact area of expertise. And so I kind of switched gears and just started educating on public health and nutrition science and kind of helping people to connect some dots with how policy is impacting some of these things. And that's kind of like where the shift happened was about a year ago. And then my account grew quite a bit since, I would say, since November of last year.
That's great. And by MAHA, you mean the Make America Healthy Again movement, led by RFK Jr. So one of your more recent videos discusses correlation and causation, which is always a challenge for a science teacher like myself. It's so important for people to understand. You used shark attacks and ice cream sales as the
Mhm.
as the example, which I loved. Can you give us a little bit of insight on that correlation versus causation video?
Yeah, I think it's one of the most important things that you can understand. And sometimes seems like, oh, I just have to learn this for my research methods class. But no, it's actually very important, especially in the current media environment we're in, to kind of like discern some of these things. And I see it all the time on social media being conflated, where people will make really big like fear-mongering videos using correlational data as if that shows causation. So one of the best examples, and I used to use it when I was a professor as well, is this idea of shark attacks and ice cream sales. So if you look at a graph of shark attacks and ice cream sales, they're pretty aligned, right? They correlate with one another very strongly. As ice cream sales go up, shark attacks go up, and as ice cream sales go down, shark attacks go down. It's really important to understand that's correlational data. So if I put that on the screen and I say, and I show it to you and I say, oh my gosh, look at this relationship. And I try to like, create policy basically saying that, okay, well, because these things are rising at the same time, what we should do is we should ban ice cream sales to prevent shark attacks. When I say that to you, that sounds ridiculous, right? But that's what's done often on social media is they'll take two things that are correlating with one another and they'll say, okay, well, this must be causing this, so we'll remove this in order to change that. And that's just not the way that it works, right? So if you ban ice cream sales, as we all know, shark attacks are not going to go down. The reason that those two things are correlated is because of something called a confounding variable, which is a variable that kind of impacts both of those things and creates that correlation. So the confounding variable is it's summertime, right? As the weather gets hotter, shark attacks go up and ice cream sales go up. More people are at the beach, more people are buying ice cream. As the weather gets colder, both of those things go down. And so when you think about if you ever see like a graph put up and you see like two things that are correlated, another example I used in that video was organic food sales and autism rates, and I graphed it over time, right? And so this is oftentimes how people do things and when they're trying to kind of promote propaganda, right? They'll look at over time, so they'll look at like over the last 50 years, the two things that have increased together, and the confounding variable is time, right? The only reason that they have both increased is because both of those things increased over that same period of time. So organic food sales have increased significantly over the last few decades, and autism rates have increased significantly over the last few decades. When I graph those together, that looks pretty compelling. But the thing is that's just a correlation. It's not a causation. So correlations are very important in science because that's observational data, and that's how we start to derive a hypothesis, right? And a hypothesis is a research question. So if we see that organic food sales and autism rates are increasing, we could say, oh, would that be a good research question? Could organic food sales potentially be causing autism? And then you would have to think, okay, is there some sort of mechanism of action for that? And then you could design a research study, like something like a randomized controlled trial that's actually designed in order to show causation. But without that data, you can't say those two things are causing one another. You can say they're correlated, but I mean, lots of things that are completely unrelated are correlated.
It'd be kind of fun to make that study where we just give people ice cream and then throw them into the ocean and see what happens.
Yeah.
See if there's actually any causation there. And what you're talking about is all about scientific literacy. We can see
Yeah.
on social media what people like the Maha movement are doing to mislead people in their disinformation campaigns and things like that. And that's really the thing that's the most important thing. And I think that this dangerous rise, like the anti-vaccine movement, very dangerous rise of pseudoscience in the United States is bad for all of us.
Hmm.
But if you don't mind, I want to ask you something before we go about your Substack. You posted something on Substack in April that is very important for us out here in suburban Philadelphia right now, and you actually posted a video on it very recently on PFAS. I should tell people, if you don't know what Substack is, it's an online platform that allows writers and creators to publish newsletters, podcasts, and other forms of digital content directly to their subscribers. So basically, PFAS, which stands for per and polyfluoroalkyl substances, is a big concern where I live. Can you give us the gist of what PFAS are and what the current government is doing that should concern us?
Sure, yeah. So PFAS are often termed forever chemicals because they've been found to not break down easily in the environment or in the human body. So whether or not they don't break down at all, I'm not sure on that, but it's difficult to break them down. And they're man-made chemicals. So they come from things like nonstick, like cookware, fast food wrappers, even cosmetics. I mean, they're in a lot of different things.
Here,
And
if I,
so,
if I could just like break in for a second, here
yeah.
where we are in suburban Philly, one of the places we're getting it most in our groundwater is from firefighter training, where
Yes.
it's in the flame retardant chemicals they use to fight fires.
Yeah, the biggest places people are really exposed to these things, and it varies depending on area. So that might be big for you guys. But drinking water is a big one, and from firefighters is a big source as well. Food from like PFAS treated like packaging and things like that. Those are probably the two biggest ones. It's also like in the dust. You also absorb it if cosmetics kind of contain them. So anyway, what had happened was under the Biden administration, for the first time, they decided to put limits to the amount of PFAS that can be in drinking water. Now, there's thousands of these, but there's some that have been shown that are stronger researched than others and that have been shown to be linked to some of these health consequences. And so what they wanted to do was put limits on 6 of the bigger ones. Some of the utility companies sued the Biden administration, and so they ended up in court. And their goal was to fight that in court. That was kind of near the end of the Biden administration when that happened. When the Trump administration came in, what they just did at the EPA, they rolled back those drinking water standards. They said that they weren't going to put any of that in for 4 of them, so they were just going to get rid of them for 4 of them. And for 2 of them, they pushed back the date that these companies would actually have to abide by the standards, I think until 2031, to kind of, I think, probably buy them some more time. So unfortunately, a lot of us would like to see stronger limits on things like these forever chemicals. But the Trump administration right now is really pushing this kind of deregulatory agenda at the expense of cutting down on some of these pollutants in our air, soil, and water.
That is what it seems like is going on. And unfortunately, we don't know 100% what these chemicals are doing to people. And it's pretty scary out here being in the water. But thank you for expanding on that for us. So, Dr. Jessica Knurick, you've been incredibly generous with your time and expertise today. So I don't want to take any more of it. If we could just end with this, if you had one thing you'd like to tell undergraduate anatomy and physiology students, what would it be?
I think maybe the topics that you're learning about that seem like you just need to learn them for the test or for the exam, you actually will find as you go through that everything that you're learning about in your science classes is improving your scientific literacy, and that's going to carry through with you throughout every aspect of your life. You're going to be able to discern fact versus fiction. You're going to be able to identify misinformation when people are trying to mislead you in all different areas. And because many of us go to social media for our information now, and because social media is this place where a lot of people can make a lot of money, these social media algorithms really rely on this like misinformation, these conspiratorial content, and that's what they push out into the algorithm. And so you'll be able to identify that a lot easier with the kind of skills that you're learning through your science courses right now. So that's what I would say, just kind of remembering that you're learning how to learn right now, and that's the most important thing that you can learn through your studies.
Well, I couldn't have said that better myself. So once again, thank you so much. I really appreciate you coming on and sharing all of this amazing knowledge. And thank you for fighting the good fight the way you are. I really think you're making a difference.
Thank you so much for having me. I appreciate it.
Thanks again, Dr. Knurick, for coming on. I hope the listeners got as much out of that conversation as I did. What an honor. Having said that, let's get back to the digestive system. I posted some images on Instagram that will help you follow along with the content if you can. Okay, let's start talking about the small intestine, and we're going to start with the anatomy. The small intestine is the principal site of digestion and nutrient absorption and represents the longest segment of the digestive tract, measuring approximately 6 meters in length. It is anatomically divided into 3 distinct regions: the duodenum, which is sometimes called the duodenum, jejunum, and ileum, each with unique structural and functional characteristics, yet they all share a common histological architecture designed to optimize nutrient processing. We'll get into specifics of chemical digestion later on, but we'll touch on it a little bit while we discuss the anatomy of the small intestine. Let's start with the shortest and most proximal segment, the duodenum. It forms a C-shaped loop that encircles the head of the pancreas, which is deep to the stomach and also retroperitoneal. It's located primarily in the upper right abdomen and mostly retroperitoneal. The duodenum receives chyme from the stomach as well as secretions from the liver and pancreas. These secretions, which are rich in bicarbonate, bile salts, and digestive enzymes, initiate the final stages of chemical digestion. Duodenal glands, which are sometimes known as Brunner's glands, are in the submucosa and secrete alkaline mucus to neutralize gastric acid and protect the mucosa. Importantly, the duodenum is the site where pancreatic zymogens such as trypsinogen, chymotrypsinogen, procarboxypeptidase, and proelastase are activated by enterokinase on the brush border. Enterokinase is an enzyme secreted by the brush border cells of the duodenum. Once activated, these enzymes catalyze the breakdown of proteins into absorbable units. Carbohydrate digestion continues via pancreatic amylase and other brush border enzymes, while pancreatic lipase, aided by bile, emulsifies dietary fats. The duodenum also absorbs select nutrients, including iron and calcium, along with water and electrolytes. The next section is the jejunum. The jejunum follows the duodenum and occupies the upper left quadrant of the abdomen. It is characterized by tall, slender villi, or villi, abundant plicae circularis, and an extensive capillary network, which together greatly enhance absorptive capacity. While it does not secrete zymogens, the jejunum facilitates ongoing digestion and is the primary site for absorption of most nutrients, including monosaccharides, amino acids, di and tripeptides, fatty acids, and both fat and water-soluble vitamins. Lipids emulsified into micelles by bile salts are absorbed by enterocytes and packaged into chylomicrons, which enter the lacteals of the villi for transport via the lymphatic system. You might want to go back and listen to the lymphatic episode a little bit to review what lacteals are. Remember, entero means intestine, so an enterocyte is the epithelial cells lining the lumen of the intestines. The ileum is the final and longest segment of the small intestine. It transitions to the large intestine at the ileocecal sphincter or valve. Histologically, the ileum displays shorter and sparser villi compared to the jejunum and contains numerous goblet cells and prominent aggregated lymphoid nodules that are involved in immune surveillance. We discussed these also in the lymphatic episodes, and they're sometimes referred to as Peyer's patches. The ileum's primary absorptive roles include the reuptake of bile salts and the absorption of vitamin B12, which requires binding to intrinsic factor produced by the stomach. The ileum also continues to absorb water, electrolytes, and residual nutrients. To support efficient digestion and absorption, the small intestine's lumen is equipped with 3 levels of surface area amplification. I mentioned these a little bit earlier, but now I'm going to talk about them a little bit deeper. The first are the plicae circularis, which are transverse mucosal folds that can be seen with the naked eye. They increase the surface area of the lumen by wrinkling up the luminal surface. Then, if you look microscopically, you'll see those villi, the finger-like projections of the mucosa. and each of the enterocytes on the villi have microvilli, and they form the brush border. These adaptations maximize the capacity for absorption by expanding the surface area exponentially.
Bombas makes the most comfortable socks, underwear, and T-shirts.
Warning, Bombas are so absurdly comfortable you may throw out all your other clothes.
Sorry, do we legally have to say that?
No, this is just how I talk, and I really love my Bombas.
They do feel that good. And they do good, too. One item purchased equals one item donated.
To feel good and do good, go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
All right, since we're going to talk about chemical digestion in the intestine later, now I want to get into the accessory organs of digestion, specifically the ones that are in the abdominal cavity, the liver, the pancreas, and the gallbladder. We'll start with the liver. The liver serves as a vital accessory digestive organ responsible for the synthesis and secretion of bile, metabolic regulation, detoxification, and numerous endocrine and hematologic functions. Located in the upper right quadrant beneath the diaphragm, the liver consists of 4 anatomical lobes: right, left, caudate, and quadrate. It's also organized into functional segments based on blood and bile flow. The liver's histological unit, called the hepatic lobule, features a central vein surrounded by plates of hepatocytes and large capillaries called hepatic sinusoids. They carry mixed blood from the hepatic artery and the portal vein. Liver cells are called hepatocytes and carry out a range of tasks, including bile production, nutrient metabolism, plasma protein synthesis, and detoxification. The liver's capillaries, called sinusoids, are lined with fenestrated endothelial cells that have large gaps between them. These larger than usual intercellular clefts allow the blood plasma to come in contact with the hepatocytes. This allows the liver cells to absorb vitamins, iron, amino acids, glucose, and other nutrients from the blood plasma. Remember that the blood that's coming from the digestive tract organs is going into the hepatic portal, which is going to the liver before it re-enters the general circulation. Hepatocytes also secrete albumin, angiotensinogen, clotting factors, and lipoproteins into the blood. Star-shaped macrophages, called stellate macrophages, are also known as Kupffer cells, and they are the liver's resident phagocytes. They remove bacteria and debris from the blood. So remember, I just said that the GI tract sends its blood to the hepatic portal vein, not the inferior vena cava. The hepatic portal vein brings blood to the liver, so materials we absorbed in the GI tract can be processed, stored, detoxified, etc. We don't want all the things that you consume to be going right into your general circulation so they can reach your brain and your spinal cord and all your other organs that they might be damaging to. So the liver has to process all the things you consume before it can release it into the general circulation. Each hepatic lobule has several sinusoids associated with it, and a small branch of the hepatic portal vein leads to each hepatic sinusoid. Next to that branch is a branch of the hepatic artery proper that brings the liver its own blood supply, and a bile ductule. That's a small duct that eventually merges with others, forming the left or right hepatic duct. The left and right hepatic ducts merge to form the common hepatic duct, which is carrying bile. Each set consisting of a branch of the hepatic portal vein and the adjacent branch of the hepatic artery proper and a bile ductule is called a hepatic triad. And these are found between all the hepatic lobules. So let's talk about bile for a bit. Hepatocytes secrete bile, which is a fat emulsifier. We're going to talk about its specific function in detail later, but let's go over how bile gets from the liver to the duodenum. Bile drains into the tiny bile canaliculi, which lead to a bile ductule that eventually reaches the common hepatic duct, as mentioned earlier. From there, it either flows into the duodenum or is stored in the gallbladder. As the common hepatic duct passes by the gallbladder, the cystic duct coming from the gallbladder merges with it. The two become the common bile duct, which then travels to the duodenum. Before emptying into the duodenum, the common bile duct merges with the pancreatic duct at the hepatopancreatic ampulla. We'll talk about the pancreatic duct a little bit later. A circular band of smooth muscle called the hepatopancreatic sphincter regulates the flow of bile and pancreatic secretions into the duodenum. If this sphincter is closed, the bile backs up toward the liver but turns into the cystic duct and further into the gallbladder where it is stored and concentrated. Bile composition includes bile salts, bilirubin, cholesterol, phospholipids, and electrolytes. Since the gallbladder is a fluid-filled sac, it's a cyst. Since bile is cholesterol-based, we use the prefix cholecyst to refer to the gallbladder. Let's talk about the gallbladder a little bit, which does not produce bile. It just stores it and concentrates it and then releases it into the duodenum. Histologically, the gallbladder's mucosa is lined by simple columnar epithelium with apical microvilli, designed for absorbing water and electrolytes to concentrate the bile. The muscular layer, although irregular, contracts in response to the hormone cholecystokinin, or CCK, which is released by the duodenum after ingesting fatty foods. CCK also relaxes the hepatopancreatic sphincter so the bile can enter the duodenum. Common gallbladder conditions include cholelithiasis, which is gallstones, and cholecystitis, which is inflammation of the gallbladder. A cholecystectomy is the removal of the gallbladder. Beyond its digestive contributions, the liver is also a hub of non-digestive physiological processes. It helps to regulate blood glucose via glycogenesis, which is the production of glycogen, which means stored glucose, glycogenolysis, which is the breakdown of glycogen, meaning we release glucose into the bloodstream, and gluconeogenesis, which is when we take non-carbohydrate sources and we convert them into glucose. It synthesizes lipids and lipoproteins, catabolizes amino acids, and detoxifies ammonia via the urea cycle. It produces most plasma proteins, including albumin, clotting factors, and carrier proteins. It inactivates drugs and hormones. It participates in immune function, clears red blood cells, and it stores several vitamins, including A, D, B12, and K. Okay, so now let's talk about the pancreas. The pancreas is a retroperitoneal gland with both exocrine and endocrine functions. It lies posterior to the stomach, or deep to the stomach, and extends from the duodenal curve to the spleen, which is all the way out on the left upper quadrant, inside of your lower ribs. Its exocrine portion is 99% of it, and it is composed of acinar cells that produce digestive enzymes, many of them as zymogens. It also has ductal cells that secrete bicarbonate. Remember that the pancreas is both an exocrine and an endocrine gland. We talked about its endocrine function in the past in terms of the hormones it produces and releases, like insulin and glucagon. Along with water and other electrolytes, the bicarbonate, enzymes, and zymogens form what is known as pancreatic juice. The main zymogens, trypsinogen and procarboxypeptidase, are activated in the duodenum, while amylase and lipase are secreted in active forms. The bicarbonate neutralizes gastric acid, providing the optimal pH for enzymatic activity. Remember, acid denatures proteins, so we want the enzymes in tip-top shape so they can do their job. Pancreatic secretion is regulated by vagal input and hormones, such as cholecystokinin, stimulating enzyme release, and secretin, stimulating bicarbonate secretion. Check out episode 37 if you want to review the endocrine function of the pancreas. We're going to talk more about the pancreas when we get into the chemical digestion in terms of what those enzymes do. But remember that the pancreas has a head, which is tucked into the crook of the duodenum, a body which heads out laterally to the left side, and a tail, which is the end of the pancreas over on the spleen side in that left upper quadrant. Running the length of the pancreas is the pancreatic duct. So the acinar cells secrete their exocrine secretions, their digestive enzymes, their pancreatic juice, into small ductules that all lead to the pancreatic duct. And that pancreatic duct runs all the way from the tail to the head, merging with the common bile duct coming down from the liver and gallbladder. We talked about that a little bit earlier. That merges at something called the hepatopancreatic ampulla, a little swelling of those two ducts coming together. And that is regulated by the hepatopancreatic sphincter, which is a circular band of smooth muscle that will contract, cutting off that ampulla, or dilate, opening it so pancreatic juice and bile can enter the duodenum. Now, there's a little branch coming off the pancreatic duct superiorly called the accessory duct. This duct does not merge with the common bile duct. Instead, it goes directly into the duodenum without a sphincter. So even if that hepatopancreatic sphincter is contracted and closed, pancreatic secretions can still enter the duodenum without having to worry about being delayed. Because it's super important for those pancreatic secretions to make it into the duodenum. I'm going to post some images as usual on Instagram so that you can follow along with some of this anatomy. Sometimes you'll hear people call the hepatopancreatic ampulla the ampulla of Vader, V-A-D-E-R, and they'll call the hepatopancreatic sphincter the sphincter of Oddi, O-D-D-I. Those are the old eponyms named after people that we don't really use so much anymore academically, but you'll probably hear it if you're working in the field. All right, so together, the small intestine, liver, gallbladder, and pancreas form a tightly integrated system orchestrating the complex processes of digestion, nutrient absorption, metabolic regulation, and homeostasis. Understanding their anatomy, histology, and physiology provides critical insight into gastrointestinal and systemic health. All right, so we talked a lot about the structure of these organs. Now we need to talk about the function of their secretions. By the time food residue transitions from the small intestine into the cecum, the processes of chemical digestion and nutrient absorption are largely complete. Before exploring the functions of the large intestine, we should discuss the pathway and transformation of the primary classes of macronutrients, carbohydrates, proteins, and fats, from ingestion to absorption. Remember that most chemical digestion is carried out by enzymes, and most enzymes end with the suffix ase, so their word ends with the sound ase, like peptidase, lactase. You've probably heard of some of those. So we're going to talk about each of the macronutrients and how they're broken down in our bodies. We'll start with carbohydrates, as you may know them as carbs. Let's take a minute to review the basics of carbohydrates first. Carbohydrates are essentially sugars and starches. In the human diet, we see them in breads, pasta, cereals, grains, rice, vegetables, fruits, sweets, and other similar sources. The simplest carbohydrates are the monosaccharides. Mono for one. These carbohydrates are molecules with 24 atoms each, 6 carbon, 12 hydrogen, and 6 oxygen. C6H12O6. That's the chemical formula. There are 3 monosaccharides of importance to us: glucose, galactose, and fructose. They're all C6H12O6, but the arrangement of the atoms is different from one to the other. A disaccharide is a compound with 2 monosaccharides bound together. For example, maltose is 2 glucose molecules. Sucrose, which you know as table sugar, is glucose and fructose. And lactose, or milk sugar, is glucose and galactose. Oligosaccharides are carbohydrate chains consisting of at least 3 monosaccharides, but usually not more than 50. Once the chain has more than 50 monosaccharides in it, it's typically referred to as a polysaccharide. Glycogen is the form that animals use to store polysaccharides, while starch is how plants store polysaccharides. Finally, cellulose is the structural polysaccharide found in the cell wall of plants. Humans do not produce enzymes that digest cellulose. Therefore, cellulose is indigestible and acts instead as a dietary fiber. Now, I know that you're thinking, but we eat a ton of plants. How are we not digesting their cell walls? We'll talk about that more in the large intestine episode because mostly microbes that live in our gut digest it for us. Okay, now that we have that down, we can talk about how we process carbohydrates. Starch is the main digestible carbohydrate in the human diet. Glycogen appears only in trace amounts in our food and is digested in the same way starch is. Carbohydrate digestion begins in the oral cavity where salivary amylase first cleaves the starch into oligosaccharides, each consisting of a chain that is 8 glucose residues long. A glucose residue is a single glucose molecule within a larger molecule, like a polysaccharide or glycoprotein, which is a carbohydrate bound to a protein. Salivary amylase operates optimally at a near neutral pH, 6.8 to 7.0, allowing it to function effectively in the mouth. Once in the stomach, this enzyme is quickly inactivated by the hydrochloric acid of gastric juice unless it is sequestered within the core of a food bolus, where it can persist for up to 2 hours. This activity is prolonged especially in larger meals and within the stomach's fundus, where gastric mixing is slower than in other parts of the stomach. However, as digestion progresses and the bolus breaks apart, the enzyme is exposed to acid, denatured, and broken down by the protein-digesting enzyme pepsin. Roughly half of dietary starch is digested prior to reaching the small intestine. Upon entering the duodenum, pancreatic amylase takes over the digestion of carbohydrates, rapidly converting starch into maltose and oligosaccharides within 10 minutes. The final steps occur at the brush border, which is the microvilli of the small intestine's simple columnar epithelial cells. These cells are called enterocytes, as I mentioned before. The brush border secretes 3 enzymes: dextrinase, glucoamylase, and maltase. Dextrinase and glucoamylase cleave the oligosaccharides that are more than 3 glucose residues long, while maltase hydrolyzes maltose. Recall that hydrolyze means to break down by a chemical reaction with water. The ultimate product of these brush border reactions is glucose, which is then absorbed by the enterocytes. As for the other disaccharides, sucrase breaks down sucrose into glucose and fructose, while lactase digests lactose into glucose and galactose. These monosaccharides are immediately absorbed. You may have heard of people who are lactose intolerant, or maybe you are. Most mammals don't drink milk past infancy, and only humans drink milk from other species. So in most of the human population, lactase production declines after early childhood as expression of the gene that codes for lactase wanes. So lactase synthesis declines and lactose ends up being indigestible. That's lactose intolerance. I've often wondered about drinking cow's milk and why we do that. I like milk, but it is kind of weird, right? I mean, who was the first person to look at a cow and think, I'm going to drink whatever I can squeeze out of that? Anyway, back to lactose intolerance. This genetic pattern is prevalent among populations with no historical dependence on dairy, such as many Africans, Asians, and Mediterranean peoples. In contrast, populations from Western and Northern Europe, Mongolia, and select pastoral African tribes, as well as their well-traveled descendants, have been using milk from domestic animals for thousands of years. So many of them exhibit lactase persistence due to genetic mutations, meaning they continue to make lactase. Environmental factors also contribute, as some individuals can gradually acquire a tolerance to dairy. Undigested lactose entering the colon increases the osmolarity of the lumen, resulting in water retention and then diarrhea. Colonic bacteria ferment lactose, producing gas, cramps, and flatulence, which is the gas we expel, and that's really uncomfortable. Nonetheless, lactose-intolerant individuals can often tolerate yogurt and cheese where bacterial fermentation has broken down much of the lactose, or they can consume dairy while also taking lactase supplements. The absorption of monosaccharides occurs rapidly via enterocyte transport proteins. Glucose and galactose utilize sodium-glucose transporters similar to those we discussed in the renal tubules. Once inside the enterocyte, glucose is released into the extracellular fluid, raising osmolarity and drawing water across tight junctions via osmosis. This water flow, or solvent drag, carries additional nutrients such as glucose. After carbohydrate-rich meals, solvent drag significantly enhances glucose uptake beyond that mediated by sodium-glucose transporters alone. Fructose, by contrast, is absorbed by facilitated diffusion through a sodium-independent carrier. Most fructose is converted to glucose within the enterocyte. Glucose, galactose, and any remaining fructose exits the basal side of the enterocyte by facilitated diffusion and enters the capillaries of the intestinal villi. From there, the hepatic portal system transports them to the liver.
Bombas makes the most comfortable socks, underwear, and T-shirts.
Warning, Bombas are so absurdly comfortable you may throw out all your other clothes.
Sorry, do we legally have to say that?
No, this is just how I talk, and I really love my Bombas.
They do feel that good. And they do good, too. One item purchased equals one item donated.
To feel good and do good, go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
Okay, now let's talk about protein digestion and absorption. Remember that proteins are amino acids bound together by peptide bonds and then folded into a three-dimensional shape. Two or more amino acids bound together by a peptide bond is a peptide. We have dipeptides, oligopeptides, and polypeptides. Once that peptide reaches a certain length and demonstrates certain protein characteristics, then it's considered a protein. First, keep in mind that we do not absorb whole protein molecules. In the lumen of the digestive tract, proteins must be broken down into dipeptides and amino acids before they are absorbed. Humans absorb the amino acids from approximately 75 to 90 grams of protein per day. They originate from three sources. Dietary protein accounts for about 45 to 60 grams. The remaining 30 grams or so comes from digestive enzymes that digest each other and epithelial cells that get sloughed off from the lumen surface, which are then digested by these enzymes. Proteases, also known as peptidases, are the enzymes that begin protein digestion in the stomach. Saliva contains no proteases, but gastric pepsin hydrolyzes peptide bonds, particularly those involving the amino acids tyrosine and phenylalanine. This activity results in short polypeptides and some free amino acids. Pepsin operates best in acidic conditions with a pH of about 1.5 to 3.5. When it gets to the duodenum, which has an alkaline environment due to the duodenal secretions of bicarbonate, pepsin is deactivated. The pancreatic enzymes trypsin and chymotrypsin continue digestion in the duodenum by breaking down polypeptides into shorter chains of amino acids. Then these chains are further broken down by the pancreatic enzyme carboxypeptidase and the brush border enzymes aminopeptidase and dipeptidase. Carboxypeptidase removes amino acids from the carboxyl end, while aminopeptidase cleaves peptides from the amino end. And dipeptidase splits dipeptides. Amino acids are absorbed via several sodium-dependent co-transporters. Dipeptides and tripeptides are also absorbed and broken down within enterocytes. Once free, amino acids exit the basal surface of the cells by facilitated diffusion, enter the capillaries of the villus, and are transported via the hepatic portal system to the liver, just like carbohydrates. In infants, the absorptive epithelium can internalize intact proteins through penocytosis and release them into the bloodstream via exocytosis. This mechanism allows maternal immunoglobulin A antibodies in breast milk to confer passive immunity. However, the transport of whole proteins can provoke allergic responses. With maturation, this ability diminishes significantly. Okay, now let's talk about lipid digestion and absorption. Lipids present a unique challenge due to their hydrophobic nature. Digestion begins with lingual lipase, which is an enzyme secreted by the tongue but activated in the acidic environment of the stomach, where it is joined by gastric lipase from the stomach. Together, these enzymes account for 10 to 15% of fat digestion before chyme reaches the duodenum. The larger the lipid globule, the lower its surface area, which is where it is contacted by enzymes. This is a problem for fat digestion because we want to maximize enzymatic action on these ingested fats. So we use a process called emulsification, which breaks the large globules of lipid into smaller droplets, increasing the total surface of the original globule. The first emulsification takes place via gastric churning in the stomach. The contraction of the stomach's muscularis externa physically breaks up the large lipid globules. Then, when they get to the duodenum, bile acids from the liver and gallbladder and lecithin, a component of many of the foods we eat, coat the droplets, forming stable emulsions that resist the tendency for the small droplets to come together and reform into large globules. Think about a layer of oil in a bottle of water. You can shake it up and the oil will break apart into small droplets, but let it sit there and it will all come back together to form the layer again. That's what we want to avoid. Intestinal segmentation, the contraction of circular muscles, further reduces droplet size to about 1 micrometer. Pancreatic lipase, present in large quantities, rapidly digests triglycerides into 2 free fatty acids and 1 monoglyceride. These products are more membrane permeable than intact triglycerides and therefore are easier to absorb. Micelles, tiny bile acid aggregates, transport lipids to the enterocyte surface. Each micelle contains bile acids with hydrophilic exteriors and hydrophobic interiors. They carry cholesterol, fat-soluble vitamins, and the products of lipid digestion. When they contact with the intestinal epithelium, micelles release their cargo, which is absorbed either by simple diffusion or through carrier-mediated mechanisms. The micelles then recirculate to ferry more lipids. In the absence of micelles, fat absorption efficiency plummets to below 50%. Once inside the enterocyte, fatty acids and monoglycerides are reassembled into triglycerides within the smooth endoplasmic reticulum. The Golgi complex packages these with cholesterol and phospholipids into chylomicrons, lipid protein complexes ranging from 75 to 1200 nanometers in diameter. Via exocytosis, chylomicrons are released into the core of the villus, where, because of their large size, they enter lacteals of the lymphatic system instead of blood capillaries. Lymphatic vessels carry chylomicrons through the cisterna chyli and thoracic duct, where they're deposited into the bloodstream at the left subclavian vein. Again, review the lymphatic system if you're not sure what all that means. When we eat plant or animal products, we're often consuming their DNA and RNA. So we have to break down these nucleic acids into smaller, more absorbable parts. Nucleic acids are not nearly as large a part of our diet as proteins, carbohydrates, and fats. But they're still in there. So let's talk about nucleic acid digestion. Dietary nucleic acids are broken down into nucleotides by pancreatic nucleases, RNA by ribonuclease, and DNA by deoxyribonuclease. You probably could have guessed that. Remember that a nucleotide is made of a sugar phosphate backbone and a nitrogenous base, like thymine or cytosine, for example. Brush border enzymes called nucleosidases and phosphatases further decompose the nucleotides into phosphate ions, nitrogenous bases, and simple sugars, which are then absorbed. In addition to the macronutrients, we also get vitamins and minerals from our food. Vitamins are absorbed without digestion. Fat-soluble vitamins, A, D, E, and K, are incorporated into micelles along with lipids, requiring dietary fat for effective absorption. Water-soluble vitamins like B vitamins and vitamin C are absorbed by simple diffusion. Well, except for vitamin B12, this is an exception. It must bind to intrinsic factor in the stomach to be absorbed in the ileum via receptor-mediated endocytosis. Mineral absorption occurs throughout the small intestine. Sodium ions are absorbed with glucose and amino acids. Chloride is exchanged for bicarbonate in the distal ileum. Potassium is absorbed via simple diffusion and can be lost in diarrhea, potentially causing fatal hypokalemia. That's low potassium in the blood. Iron absorption is tightly regulated. When iron ionizes, it can give up either 2 or 3 electrons, meaning there are 2 ion forms: ferrous ions, which have a +2 charge, and ferric ions, which have a +3 charge. Only ferrous ions are absorbable. Gastric acid in the stomach converts dietary ferric ions into this form. Inside enterocytes, iron binds one of two proteins, transferrin for transport or ferritin for storage. Iron is primarily stored in the liver, and too much iron in the blood can be toxic. So the liver produces a hormone called hepcidin, Hepcidin, which suppresses iron absorption and release. In conditions of anemia or hypoxia, hepcidin production is reduced, allowing increased iron uptake and mobilization. Calcium is absorbed actively in the duodenum through a process dependent on vitamin D and parathyroid hormone. Calcium enters via channels, binds to calbindin, and exits through ATP-dependent and antiport transporters. In the jejunum and ileum, calcium is absorbed paracellularly and independent of hormonal control. Calcium bioavailability is reduced in the presence of dietary oxalate and unabsorbed fats. Oxalates bind to calcium and prevent them from being absorbed. They're found in foods such as spinach, almonds, beets, and soy products. It doesn't mean you shouldn't eat those things, but keep in mind that if you eat those things with sources of calcium, you're going to get less absorption of that calcium. Finally, water absorption. The digestive system handles approximately 9 liters of water daily. About 75% of that is gastrointestinal secretions. The rest comes from what we eat and drink. Of this, about 8 liters are absorbed in the small intestine and 0.8 liters in the large intestine. The rest is excreted with feces. Water follows solute absorption by osmosis, moving from the lumen to the extracellular fluid. Diarrhea results from insufficient water absorption, often due to rapid transport through the GI tract, irritation of the mucosa, or osmotic imbalance like undigested lactose. Constipation arises from excessive water reabsorption, slowed GI transit, or insufficient fiber and/or hydration. When digestion in the small intestine is complete, nutrients have been chemically broken down and absorbed through intricate, tightly regulated processes, prepping the residue for final processing in the large intestine. But I think I'll leave the large intestine to the next episode. That was a lot to take in. I'll also discuss the blood supply to the digestive system in the next episode and motility. That should wrap up the digestive system. Once again, thank you very much to my special guest, Dr. Jessica Knurick. You can follow her on Substack and all social media platforms. I will post links in the show notes, but to find it all, go to jessicaknurick.com. That's Knurick with a K, Knurick. That link will be there too. She is leading the fight for scientific literacy right now, and we are all better for it. As usual, I hope this podcast is helping you get your beer better in A&P, or simply helping you understand how our bodies work. Good luck, and I'll talk to you next time. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media. Please take the time to rate the podcast, and don't forget to check out my YouTube channel, Student Help for AP. That's Student Help, the number 4, AP. There's a whole lot of tutor videos on there that I think you're going to find helpful. Special thanks to my family, Bucks County Community College, and McGraw-Hill Education, where you can find Anatomy and Physiology Digital Suite, my low-cost, tutor video-based digital learning solution for anatomy and physiology, already being used at several colleges and universities.